Alrighty, so astronomy and astrophotography are really cool hobbies, but a lot of the off-the-shelf equipment is really expensive. Well, I had a 3D printer and a lot of spare time, so I decided, why not make my own? Introducing the Open Smart Focuser, a 2-inch linear focuser with some pretty neat features built in. It's fully 3D printed, open source, and compatible with software such as Indie, with ASCOM support in the future, and it can be assembled for less than most commercial focusers on the market. The main housing is 3D printed along with the draw tube and end cap. Additionally, the worm drive is also designed to be 3D printed. The housing uses the same 120mm fan holes as a PC fan to allow for easy adaptation to existing optical tube assemblies, as well as native compatibility with my Open Smart Scope design. For your non-3D printed hardware, you just need two 100mm linear rails and carriage blocks, a dual start lead screw, and a NEMA 11 stepper motor, and some bearings, screws, and buttons. The drivetrain uses the NEMA 11 connected to a 23:1 worm drive, which spins the brass nut around the lead screw to drive the draw tube up and down. This delivers around 36,000 steps per millimeter, giving a theoretical resolution of about 27 nanometers per step for extremely fine precision control. Obviously, with 3D printed worm drive and other 3D printed components, there will be some play. But for astrophotography, it's more than capable of competing with high-end commercial focusers. Everything is driven by a custom ESP32 PCB with a TMC 2209 stepper and power module. The PCB was provided by the sponsor of today's video, PCBWay. My previous designs used a perf board, which is great for initial prototyping, but I wanted a nice, smooth, and sleek design for the final focuser build, and PCBWay was gracious enough to help me achieve this. After converting my initial prototype into a PCB, they were able to produce the boards for me, complete with assembly of components. Ordering the boards was extremely simple. I just uploaded my Gerber files directly to PCBWay's website, along with the bill of materials and pick and place files for assembly, and I specified the requirements for the board. After that, PCBWay's engineering team did a quick double check on my files, and it was off to fabrication. The PCB assembly service was also very helpful. I don't have a reflow station, so I wouldn't have been able to assemble those components. The boards arrived quickly and were high quality. And once I had soldered on the USB-C port, the display, and buttons, I just needed to tweak the firmware for the new board and flashed it. After powering on the focuser, everything seemed to work fine, but I soon found a few problems in my design of the power module. First, the 5-volt power rail was only outputting 3.7 volts. This is because I had miscalculated one of the buck converter's sense resistors. But the bigger issue was with the TMC driver. I don't know exactly what's wrong with it, but it's likely caused by incorrect charge pump capacitors or poor ground return, which causes the chip to reset when I'm commanding movements. To bypass this, I connected the TMC driver module from my original perf board prototype to the new PCB using a breadboard and power supply. I am currently working on an updated power module that will fix both problems for future builds. The software for this project is also open source. It's written in C with Platform IO and VS Code. It's fairly simple in its current state. The motor control is handled by the FastExcel Sever library on Core 0, with the main menu, serial communication, add-ons, and pretty much everything else handled on Core 1. The serial protocol is entirely custom. It uses command framing similar to the LX200 protocol, but that's where the similarities end. Everything was tailored specifically for this focuser and its add-ons in mind. By leveraging the ESP32-S3's native USB, I was able to assign some custom hardware and product IDs. allowing for custom Linux UDEV rules to consistently identify the correct serial port. The main display allows you to control the focuser without the need for a computer. The idle display has a nice little star map that will show you the brighter stars around your target when you're connected to a computer. It's a nice little star map that's right on the side of your scope. While in the idle screen, the up and down buttons will move the focuser in and out. And you can adjust the speed through the settings menu. There are speed settings ranging from fine, which is exceptionally slow for very precise focus adjustments, to max, which runs the stepper at just below stall speeds to allow for larger moves. There is also a built-in homing routine. And 12 presets you can either set through the command line or through the main menu. This allows you to set your focus position for 12 different filters or optics. I personally use this feature to always return to the fine focus position, so my stars are perfectly in focus at the start of my imaging session. I've installed the focuser onto the Open Smart Scope to demo the add-ons. With the base focuser, it's a very versatile device, but the ESP32 has a lot of power and pins that aren't being used, and I wanted a few additional features. The first add-on is a simple shutter. It just uses a servo connected to any of the available digital pins and the 5-volt power rail. It can open and close a shutter flap that can be designed to adapt to pretty much any optical tube assembly. And the main housing on the focuser has a convenient little spot for the shutter add-on cable. Additionally, the shutter can also hold a flat panel, either using an addressable LED strip such as NeoPixels, or a regular LED strip using a transistor, and that can be selected with just a simple solder bridge on the back of the PCB. I'm also developing an I2C sensor module for internal temperature, humidity, and ambient light monitoring. That will connect to the expansion port by the USB-C, and the light sensor can be used to assist with flat frame calibration or to warn you if stray light enters the tube during an imaging run. While working on a motor-driven collimation add-on for the primary mirror, I realized something. Why not combine everything into a single backpack board mounted directly to the telescope? So now I'm looking into designing a board that would fit on the back of the telescope that could be modified to fit commercial scopes too, and this would contain the driver and controller for the focuser, the primary mirror collimation motors, the shutter, sensors, as well as have a Raspberry Pi 5 or a Compute Module 5 built into it, basically making an all-in-one Astro computer completely built into your optical tube assembly. Thank you once again to PCBWay for sponsoring this video. I've left a link for them down in the description of the video if you'd like to check out their services, which I'd highly recommend. I've also left the GitHub link for the OpenSmart Focuser, which has all the current firmware and the current generation of CAD files, so you can check it out.